This time on CS5, we're going to learn about image compression. You probably already know more about image compression than you think. For example, have you ever noticed that image files have different extensions? Some pictures end in .png, while others end in .jpg. Why are they different? These files are compressed differently. Image compression is the process of encoding an image in binary, hopefully in such a way that the encoded image is smaller than the original. We have two primary goals when we design this encoding. First, we should be able to encode any image with our strategy. Then, we should be able to decode the image and always get the same picture back. Our second goal is for the image to actually compress. The compressed image we use should take up less space than the unencoded image. Before we design an image compression strategy, let's talk about a basic encoding strategy. An encoding is a way to represent any information, in this case an image, in binary. We'll talk about black and white pictures because they're simpler. Let's look at this simple picture. It's made up of pixels that are either black or white. We can leverage these pixels to represent the image in binary. A 0 corresponds to a white pixel, and a 1 corresponds to a black pixel. We can list these bits as a string to represent the image. Does this encoding satisfy our two original goals? We can encode any black and white image with our technique. If we are given any encoding, along with the image dimensions, we can recreate the image. This is a good image encoding, but it's not a very good compression. We need as many bits as there are pixels in the image. If the image is large, the encoding will be very large as well. Now that we've found an encoding that works, let's try to make it more space efficient. One interesting characteristic of most images we care about is that large portions of the image are similar. For example, look at these black and white images. In general, there are large blocks of white and large blocks of dark. In our original encoding, these pictures might have long strings of 1s or 0s. It would be great if there were a way to communicate a string of 100 zeros in the encoding without having to list them all out. This brings us to our first image compression strategy, which represents strings of 1s and 0s. For each block of 1s or 0s, we write down the character we want to encode, followed by the number of times it appears. For example, in our original black and white image, we started with 16 zeros. Therefore, the first bit in our encoding is a 0, followed by the binary representation of 16. If we do this for all of the strings, we see you can represent the image much more compactly. Does this compression strategy meet our two original goals? The encoding is definitely smaller than the original image. However, we might have problems recreating the image once we have encoded it. For example, let's see what happens if we are given this binary string and asked to make the corresponding picture. We see that the first color is white, but are there 2 of them, or 4 of them, or 33 of them? With this encoding, we can't always recreate the picture we started with. One solution is to introduce padding. That means we will put leading zeros in front of each number, so they are all the same length. For example, let's say we wanted the run length to all be 7 bits long. Then, our encoding would look like this. We can see that this encoding takes up more space than the last one, but it's also much easier for the computer to read. To read this encoding, we know every 8th bit represents the next color, while the 7 bits following a color bit indicate how many times we use that color. With 7 bits, we can represent up to 2 to the 7th minus 1 pixels of the same color. If we have more than that in a row, we can use the next 8 bits of the encoding to represent the leftover pixels. Our decision to use 8-bit blocks was somewhat arbitrary. We could have chosen a different number and still gotten a valid encoding. This leads to a natural question. What is the best number of bits to represent a contiguous block of black or white? The answer might depend on the picture you're trying to compress. If your picture changes between black and white a lot, like this one, then you're better off using fewer bits to encode the run length. That's because you'll waste less space on padding. If, on the other hand, your picture has large contiguous blocks of the same color, you want to use more bits encoding the run length. Then you will be able to encode each contiguous block in one run, and you won't have to split a block across multiple runs. We have seen that there is no best number of bits to encode the run lengths. In fact, we can show something rather surprising. There is no image compression strategy that will always guarantee that the compressed image is smaller than the original. To see why this is true, imagine I had an encoding strategy that took in an n-bit image and compressed it into a smaller encoding. Our compressed image now has at most n-1 bits. We can treat this as a new image and run it through our algorithm again. If we keep doing this, we can end up with a single bit. There are only two options for this bit, 0 or 1. However, there are lots of possible pictures that we could have fed into our compression algorithm, and there's no way we could create them all from a single bit. Therefore, if a compression strategy can always make its input smaller, it can't be reversed. This shows that it is impossible to design a compression strategy that always makes the input smaller while still letting us recover the original input from the compressed output. This is an important result because it means we don't have to keep searching for the perfect compression algorithm, and instead we should just focus on finding one that works well most of the time. To recap, this lecture has explained some of the mysteries of image compression. We started off by defining the goals of image compression. We want to create an encoding that uses less space, and we need to recover the original image from the encoding. We began with a naive algorithm that listed a pixel followed by the number of times it appeared. This made our image smaller, but we couldn't recreate the original image from the encoding. Next, we added leading zeros to the run length. This took up more space, but it meant the image was recoverable from the compressed file. Finally, we showed the surprising result that it's impossible to design a compression algorithm that always makes a file smaller. If we could design such an algorithm, then we could store as much information as we wanted in a single bit. Results like this are important in computer science because they show us what is and is not computable.